Hello all, welcome to the AI driven perception learning and mapping for drones course. This is the fourth tutorial for math for AI. Now the learning objectives of this particular tutorial are, we will focus more on the curve fitting example. This is something that we even saw in our lecture where we were trying to approximate a given curve. So in our lecture the curve we had was sine 2 pi x, and essentially we had training data around it, and we were trying to come up with a learning model with learnable weights w to approximate all the points on this curve. Essentially in our example we had about 10 points with some noise, and we would want to learn the proper curve of sine 2 pi x using our weights. So this is the example that we had. Essentially we had about 10 training points which are highlighted in blue here, and we can see that there are some points on the curve and some points have been added with some noise. The goal is to essentially learn for a given input x its corresponding target, which is highlighted by t. So on the x axis we have x, and on the y axis we have the corresponding target t. The true function is sine 2 pi x, which is for us to know, but it is unknown to the model. The goal is to learn the set of learnable weights w so that we can approximate this curve, right, and essentially learn from this data so that we can predict for any new x without the knowledge of the true function and any new x which could be highlighted as the test set. So let us assume that our test set consists of x cap comma t cap, which could be any point on this curve corresponding to this test sample. We would want to approximate, or we would want to get the actual target label t cap. Now essentially the task is to predict the real value target t for any given input x. The true function is something which is unknown to the model, which is sine 2 pi x, and the targets which are generated have certain noise as observed in the graph. We have about n is equals to 10 points which are uniformly spaced from 0 to 1, right. Now the key idea is to train the model which has learnable weights w to approximate the underlying function sine 2 pi x. Now this is also something we had observed in our lecture, where for m is equals to 3, that is y is given as w0 plus w1 x plus w2 x square plus w3 x cube. If we have a curve like this, essentially the fit is pretty accurate. Although it is noisy, it is supposed to be noisy, but we can observe that in this particular case the error that we would calculate, which is the vertical distances from the ground truth, would essentially be very low compared to an example of m is equals to 9. Now in m is equals to 9, the training error for us as we had observed in the lecture was essentially 0, right. So the curve actually goes and passes through all of these blue points, which is essentially all the set of training samples. However, this is an example of overfitting. So the curve shows large oscillation between the points, and hence if we would try to take a sample x cap, we would observe that the predicted t cap would not be accurate. So essentially the output for test sample x cap t cap, which are other samples except the training set on this curve, would be very very noisy, right, and hence the result is a poor generalization to the new data. Okay. Now this is also something that we had observed when this is the table essentially shows the optimal values of w for varying degree of polynomial. So for m is equals to 0, 1 to m is equals to 9, and as we discussed in the lecture also, we observe that these values are very high, right, and hence for a polynomial of degree m is equals to 9, essentially the weights would start learning the noise itself, not the actual ground truth corresponding to the training samples. Now we had also discussed, although we did not go in detail about how to get the values of these optimal weights, we do know the procedure for it. So we, in case we have a polynomial, we have y is equals to w dot x. Once we have the output, we would calculate the error which is given by E, and we would essentially want to calculate delta w. Now to find the most optimal set of weights, we would essentially try to take the gradient norm is equals to 0. If we do this particular operation and solve this particular operation, then we would essentially get the values of w. Now similarly, let us take an example of a linear model for curve fitting. So in the last example also we had a linear model in w but not in the input x. Here we have a linear model where it is highlighted by this particular matrix equation. So the first vector is essentially the input, the vector in the middle essentially highlights the learnable set of parameters which is given by a and b, and the last vector that we see of y is essentially the output, right. So we can write this particular in a simplified manner, which is ax plus b is equals to y cap. So in this example we actually identify y cap as the prediction. Now if we have the prediction and let us assume y is our ground truth level, then the mean square error, which is the MSE error, is given by 1 by n summation I is equals to 1 to n norm of EI square, which is essentially given as 1 by n summation I 1 to n yi minus yi cap whole square, right. So essentially we want to now look at this error and try to see how we can minimize this error. So if I want to write a optimization algorithm, I would essentially write arg minimum of E theta, and this essentially would give me theta star, and in this particular example our theta star is a comma b, which are the learnable weights. Now let us look at the example using MATLAB, how this affects the curve plotting. Essentially if we plot different values of x and y, which is the training sample, how can we use different values of AB to approximate or fit the particular distribution. Okay. So let us look at the curve fitting example using MATLAB. Now as discussed, let us look at a very common math problem, which is fitting a line, right. So the problem is essentially we want to come up with a linear model which is the best fit across various sample points. We essentially highlight y cap as ax plus b. In the previous slide we had denoted it using a matrix form. This is just given as a form from the equation. So y1 cap is equals to ax1 plus b, y2 cap is equals to ax2 plus b, and so on. Now the goal is to find a and b to generate the y cap, which is the prediction that is the closest to the ground truth, or essentially as the ground truth itself, right. Now again throughout the tutorial we are not focusing more on the syntax part of MATLAB. We are more interested to understand how the functions are operating and what is our overall objective. And in case you are more comfortable with Python, please you go ahead and try to do the same operations in Python. Essentially the goal is to come up with the best optimal values of a and b, right. So in this particular command, which is x is equals to line space minus 0.1 to 0.1 to 100, essentially this is trying to generate about 100 time steps from minus 0.1 to 0.1. Once we do that, essentially we generate y noisy, which is given as 5x plus 2 plus 0.5 times rand n 1 to 100. Essentially the last part is trying to generate certain noise and then add it to this particular line. So we get a plot like this. We get a plot on the right side. So we have x, we have the corresponding y, and although it seems like it is on a line, there is random noise which has been added, and this is just a way to generate the training data, right. We do not want to exactly plot a line because then the algorithm becomes trivial. So we have just added some noise to see how the best fit can happen. Now let us take a step by step approach to understanding how to get the solution. Now essentially if we focus on a trial and error method, and again trial and error method would be possible in this particular example because we have only two learnable parameters a and b. But in case we have, let us say, a very big model with say millions of parameters, then trial and error may not be the best way to go. So let us focus on the trial and error method here. The equation that fits the line best is dependent on a and b. A essentially focuses on the slope and b focuses on the intercept. Now on the right we see this graph, and in this graph we have plotted the points. Now let us assume that I change the slope. If I change the slope, we can see that the first graph highlights the slope of the line, and the second, which is b, highlights essentially the intercept, right. And I can also change the intercept to see what is its influence. So we can see this is the influence, right. And this also does give a better idea about the bias, or the importance of bias, right. I can actually have a very close approximate to this curve, but if my bias is not correct, then I see that the plotting it goes haywire, right. But essentially if I can fit the bias somehow closer to the plot, then I can see that it is a stronger approximate, right. So this is the influence of bias, which is essentially an important parameter. Now a is equals to 4 gives me this particular fit on the curve highlighted by the red line, right. We will just take one more last example. So if the slope is -7, we see that the line that is passing through does not follow the distribution at all, right. So let us assume that we keep a decent value of the slope, right. Now the graph on or the plot below actually highlights the mean square error. Mean square error is essentially all the points in x. For the values of a and b we get y cap. We now generate the distance between y cap and y. This is also something we observed in the curve plotting, which is essentially the vertical distance between the predicted value and the ground truth, right, the target. Now we can observe here that the mean square error essentially does highlight some points which is 0 because which is very close or essentially passing through these points, and for some of these points we can see that this is very high. So we can see this particular point here has a very high mean square error, right. Now if I keep changing the slope, we observe that the mean square error also keeps changing. So if the at slope of 7 we get the mean square error as 0.022. If I change the slope as -6, we can see that this drastically increases, right. And we can observe, and it is also intuitive from the either extremes in the graph. So we can see on the left part that the error is very high, and on the right part also the error is very high, and across the middle it is slightly lower because the distance is lower, right. However, one important point is this is the vertical distance that we are considering, right. It is not the closest distance from the line, but the vertical distance. Okay. Now this gives us an idea of what we want to do, and if we do a trial and error method, we can essentially try different values of a to get the least mean square error, right. And if we get the lowest error, that is essentially giving me theta star, which is essentially giving me a and b. Now once we fix the value, we can essentially compare it to the original data, and this particular command is used to generate the error, which is essentially the mean square error, right. Okay. Now right, now this is also a very interesting command in MATLAB, and it is something that gives us the solution directly. So the ML divide essentially obtains the same result. So we actually spend some time with trial and error, and let's assume that we get a good value of A and B. I can just use this particular command where x is x cap ones of 100 to 1, and essentially we try to get M, which is x slash y noisy y, right. Now essentially the goal is to get M, and essentially if you get M, this is giving you the values of A and B. So MATLAB does give us a command to do this directly, and these are the most optimal parameters for that particular sample points. Now the solution depends on the quality of the data set used, right, and this is also something we observed in our curve fitting example. We saw that if the data samples are, let's say, only one particular part of the curve. So for example, if I keep a lot of data points for x is less than 0 and I have very less number of points at x greater than 0, and let's assume it's not a linear fit, right, so it becomes like a polynomial fit, then the curve fitting is essentially very hard. So the data representation should be consistent, right. For various values of x, for various labels, we should have its corresponding samples which are essentially more diverse and more distributed uniformly. Okay. Now let's take a quick look at the gradient descent, which is something that we have been using to train our model. So the first trial and error, we saw that the parameters of the line changed, and essentially what we were trying to do is we were trying to minimize the mean square error, and this was using the slope A. So we had a line, and we know that the bias actually has an influence, but as we observe, even the slope is very important, and essentially we were trying to tune it for that. Now if we set the slope to be too high or too less, then the resulting function is unable to capture the trend, and this also applies to the parameter B, which is the bias as well, right. Now let's take a concept here where we try to essentially have B as constant and try to keep varying the slope, right. Now this is also something that we observe in the earlier curve, but this is just to give a more intuitive understanding. If B is fixed and we keep varying the slope, we can see the influence of the mean square error, right. We can see that the mean square error actually has certain values, and for certain values of the slope it is essentially in the middle, right. So if I look at this particular value, we observe that this line actually has the lowest mean square error, and essentially the optimization that we do, which is arg minimum error of theta and that would result into theta star, is essentially trying to give me this point where the error is minimum, right. This is just an intuitive way to understand the influence of both A and B, but in this particular case B is constant and we play around with A, right. Now let's take a closer look at the gradient descent algorithm. Now gradient descent is something which is basically using fundamental calculus. This is something we had discussed even in the lectures and even in the previous tutorial, and this is something which is very important, that the gradient refers to the direction of the tangent. If we reverse the direction of the tangent at a point, it gives us a direction which is towards the function's local minimum, right. And essentially the later part is just the algorithm that we know. So we try to randomly initialize the weights, calculate the reverse direction of the gradient, essentially minus eta delta w, and then since we have this derivative, we try to update the weights. Now this is also an example that we can see where let's assume that we have eta, which is a learning rate, and we try to gives different values of x to understand the curve. If we use gradient descent, we can see that although we start at a random point, using this particular logic we do come to the minimum, right. And okay, this also, so gradient descent is essentially using the fundamental calculus operations. This is something that we saw even in the previous lectures, where the gradient refers to the direction of the tangent on the curve. If we reverse the direction, it gives us the direction to the function's local minima. And essentially this is an example that we saw even earlier. This is an example we even saw earlier. What happens using the gradient descent algorithm? We start from a randomly initialized point, but we eventually go towards the minimum using this particular operation, right? And this is something that can be clearly highlighted by the by this particular video and the plot on the right. Now let us look at gradient descent in 2 dimensions. Now before we do that, let us try to see how the error surface works. So let us visualize the mean square error with parameters a and b. We had previously done it with changing only a while b is fixed. Now we draw the parameters while changing both of these values simultaneously. So when we have a constant and b varying, when we have b constant a varying, how does the error surface look, right? Now essentially this is how we get the error surface, which is plotting the values of error for various a and b, and both of them keep changing simultaneously. Now this is a 2D error surface, and essentially this is our true error surface, right? So we have the mean square error, and if we use gradient descent on this particular error surface, that could lead us to the most optimal set of a and b's, right? So just like we saw in the 1D case, let us do the gradient descent even for the 2D example. We have an example here, and this is essentially the update to the weights. So w t plus 1 is essentially w minus eta delta w, right? Eta is the learning rate, which essentially decides the step size, so how near to the curve we want to go and how far from the curve we want to go, right? How near or the further away the update should be once we have delta w. That is essentially what it means to be learning rate. Now we can, since it is a 2D problem for us and we have a and b both as learnable parameters, essentially we want to calculate the derivative of the error with respect to a, and we want to calculate the derivative of error with respect to b, right? And essentially if we look at the graph on the right, we observe that although we start from a random point, essentially it does come very quickly. Since this is a very smooth curve, it comes to a minimum value very quickly, and essentially as we keep iterating we actually get a good value of b, like we get the optimal value of b quickly. For a we keep trying different iterations, and based on the stopping conditions we get the value of a and b, right? So essentially although we are very close to the minimum, we do the optimization process until we reach this value, which is a is equals to 4.64 and b is equals to 2.06, right? So essentially even using a linear fit example, we are trying to get a good value of a and b, the optimal value of a and b, so that the error is minimum. Now let us take a similar example, but just try to see its influence. So this is the gradient descent with momentum. Now essentially the goal is to focus more on this linear model for curve fitting as we saw earlier, and try to use a momentum and see its influence. So this is the same equation that we saw earlier, right? And these are essentially the same operations also. So we take x and we essentially try to plot the value of y noisy using an approximated line and then adding some noise, right? Now to solve the problem also we saw that the mean square error for different values of a and b, right? So we will not go into this, right? This is also something which is known as the least square solution, and this is something we will focus on deriving in the next tutorial. However, it is something that you can try on first, and then maybe we can focus on how to derive this solution. So let us assume that we have a mean square error, which is the essentially 1 by n summation I is equals to 1 to n ei square, right? And this is essentially just trying to take difference between This is essentially just trying to do difference between the ground truth, which is given as y, and then y cap, which is essentially the output predictions. Now the standard solution of the above equation is highlighted as A and B is essentially x transpose x into x transpose inverse times y, right, and this is the optimal solution that we get, and from this optimal solution essentially we can minimizing the error, which is delta E is equals to 0, and then solving would give us the most optimal values of A and B, right. Now this is something that we want to check first, is this actually correct, and it is more of a homework for now, but in the next tutorial we would derive this solution. However, let us check how to do this numerically, right, like even though we have a solution here, let us see if we can get this value either by trial and error or numerically. Now again MATLAB does have this particular command which is given as ML divide, which does give us the solution of M, right. So the most optimal solution of M is essentially the A and B values, which is highlighted here. Now we have seen gradient descent, so we will skip this part for now. Now if we keep varying A and B, right, simultaneously, and if we plot the error surface looks like this, and we saw the similar thing in the previous MLX also. Essentially this is from a different view where we try to plot the error, and once we plot the error, which is a dynamic plot because it keeps changing on the value of A and B, once we plot this, then we essentially want to do our gradient optimization. Now this is a good summarization of how the gradient optimization actually works. So we try to start from a random point, essentially follow this direction and lead to a minimum, and the stopping criteria is when this particular kid gets off the ride, and this is a good summary of the gradient descent algorithm. Now this algorithm is also similar for 2D, 3D and multiple dimensional spaces. So we saw a good example for a 1D case, even in the 2D case. Now let us do a quick comparison with momentum. Momentum is essentially trying to address this solution, right. So let us say you have a very steep fall, and after that you have a very flat surface. How do we try to fasten the process, because this essentially is a very slow, it will take its own time to complete this ride, right, and this is why we use something known as momentum. Although the notations have changed, the process is more or less similar, right. Now this is the algorithm for it, which we will not go in detail, but this is very similar to what we have discussed in the algorithm that we have, right, which is essentially trying to define the error, trying to take x and y, and then trying to get the output prediction and then minimize, right. So for this particular iteration I is equals to 1 to num iter, we essentially want to pass it through gradient descent and then plot the different values, right. Now essentially the algorithm is similar with different notations. Now if we look at this curve here, and let us take a slower look, the dot in the green is essentially the momentum update, and the dot in the red is essentially the stochastic gradient update, the gradient update. Now we see that the momentum is actually pretty close to its convergence compared to the gradient descent. Now since here we have a simpler curve, the effects of learning rates are not very visible, right. So if I have a very low learning rate, it would be very slow. However, momentum would essentially try to address that particular scenario. So this the GIF that we saw earlier is essentially trying to the momentum is essentially trying to address the later part of it, where the stochastic gradient has actually become very slow. Since the gradient descent update has become very slow, using momentum would fasten the process. To summarize, we essentially went over the curve fitting example. We quickly did a recap of the curve fitting example that we saw in our lecture, followed by following a linear model, understanding the effects of learnable parameters A and B to fit the curve. We also saw the influence of different what happens when we have different slopes, which is A, and different biases, which is B, and essentially trying to plot the error for varying A and B. Once we plot A and B, the error, we kind of get an estimate of how the gradient descent algorithm would work and how to get the minimum values of A and B. Lastly, we also saw the gradient update using momentum on the same problem and trying to see its effects. Thank you.